Thank you everyone. I understand this has been a long day and I stand between you and some well-deserved rest, but thank you for taking the time and thank you Colin for that really nice presentation. Very well done. What I'm going to try and do in the next 45 minutes to an hour is to basically walk you through one component in a more detail. Right? So Colin walked through a whole bunch of different components and he talked about different components in brief. What we'll do is take a much more deeper dive into Google's compute engine, which is one aspect of the overall Google Cloud Platform. Right? So all the stuff that Colin talked about, the Google Cloud Platform is basically Google's infrastructure and services exposed to you as services so that you can build your applications on top of that, right? So all of the different services that Colin spoke about, if you put them into different buckets, you get a computation bucket, you get a storage bucket, and you get higher level services, right? On the computation bucket, you have compute engine and app engine. The app engine is the platform as a service that he spoke about. And on the storage bucket, you get cloud storage, which is object-based, cloud SQL, which is relational, cloud data store, which is NoSQL, and we have persistent disk, which is really part of compute engine, and I'll talk about that in more detail. And we have BigQuery and cloud endpoints. So together, that's the Google Cloud Platform. Everything that Google uses is the same platform that you build your application on. Your application runs on the same platforms that power YouTube, power Gmail, all this other stuff. All you're doing is taking our 15 years of experience, engineering, and investments we put into building that cloud infrastructure. We're now giving it to you as a service so that you can use it. For example, cloud data, cloud storage, it's the same stuff that backs YouTube, right? Cloud data store, that's the same thing that backs App Engine, and it handles 5 trillion transactions every month, right? And so Compute Engine and BigQuery is the same tool that Google uses to analyze its own log data. Right? In Google, you asked a question about how did an ad word perform in a geography. We use a tool to analyze that data, and we're just giving you that same tool so that you bring your data and ask questions. So what I'm going to do is now focus more on Compute Engine and go into more details on what Compute Engine is, what you can do with Compute Engine, etc. So does anybody want to take a swing and explain to me what Compute Engine is? Colin already did an explanation, so now it's your turn, right? Can you tell me what Compute Engine is? What do you think Compute Engine is? Sorry? Yeah, that's an interesting way of putting it, yeah. But essentially, it's virtual machines that you spin up in the cloud, size them any way you want. These are Linux, KVM Linux instances that you can spin up. And into that machine, into that virtual machine, you put whatever applications you want, and you can build your overall application infrastructure in the cloud. So Google kind of becomes like your data center in the cloud. That's what Compute Engine, in a nutshell, is about. So it is our infrastructure as a service offering. Google kind of becomes like a data center in the cloud, and all of that infrastructure that you see on the right-hand side there, that is just one data center that Google runs, right? One of the many that we have. And you get to run your applications in exactly the same place and in exactly the same infrastructure we use, right? And our infrastructure is easily the most scalable and efficient because that's what Google has to do to be successful as a company, right? So, why would you choose Google's Compute Engine? right? I mean, there are other public cloud infrastructures out there as well, but what makes Google's compute engine better or more relevant? A couple of things. One is the speed at which the actual compute engine instances perform, right? Think of it this way. Google designs its own server infrastructure. We own easily the world's largest fiber optic backbone, right? So, and we write all of the software around the virtualization, and we build all of these things ourselves. So what that affords us as a company and as a public cloud infrastructure provider is an ability to optimize from the bottom layer, from the networking layer to the hardware layer to the software layer, all the way up to even the browser experience. We can optimize the whole stack for speed and performance in ways that other people can't do it because they don't own the whole stack. Google owns the whole stack, and therefore it affords us a lot of opportunities for optimization that otherwise would not be. I see a lot of Mac users today, right? So it's like the difference between a Mac and a PC when you think about it. Because we own everything, you get to optimize a whole lot more. I mean, PC is good too, but what I'm saying is from the perspective of pure raw performance, we get to do a whole bunch of optimizations that it's not easy for others to do, right? In terms of having scale, depending on whatever is your workload, Google has the capacity to provide the scale that you would likely require. And that's important. Let's say you build an application and it becomes extremely popular. You need to be able to scale it up really quickly, really fast, and when maybe the load is not there anymore, you want to bring it down as well and reduce your overload. For all of those things, to be able to start up instances quickly, to be able to spin up as many number of instances as you like, Google has the scale to provide that for you. In fact, there is a very nice Google I/O talk. I think it was Urs, who's our head of engineering and technology. He actually showed a demonstration where they were spinning up machines for a genome research demonstration where they put in 600,000 cores. You look it up. It's a very nice demonstration. And if you look at the number of physical machines that translates to, that's easily about even 100,000 machines on demand just being applied to that problem. And then when the problem is done, you can remove those machines. So that kind of scale, Google can provide because we invest in roughly $3 billion every year in data centers. Right? We have a global footprint. And we have designed it from the ground up to be a global thing, and you get to take advantage of all of Google's investments in all of this fiber and a global footprint, right? For example, if you spin up an instance in Europe and an instance in America, those two instances will talk to each other on top of Google's fiber. It won't go through the public internet. Right? So that data packets that go between these two instances will ride on Google Fiber. And that gives you opportunities to build network topologies that span the globe riding on top of Google's Fiber. And that's really useful and interesting, particularly if you're building applications which want to go global. Right? So you're building an application which is local and you want to take that application global. Having that global footprint is extremely, extremely useful. And you get the rest of the Google Cloud Platform that you can take advantage of as well. So does anybody know what that car is? Tesla? No. That's right, it's a Bugatti Veyron. Right? Has anybody seen the Mission Impossible 3 movie? You know, it's the car that Tom Cruise rides in before he robs the Vatican or something like that, I don't remember. But It's an extremely fast, high-performance car. It can do something like 300 kilometers per hour top speeds. Right? Don't ask me how much petrol it consumes. I don't know. I suspect it's be likely a lot. Right? So it is an extremely high-performance machine. Do you know what that car is? That's a Toyota Corolla. Right? It's an extremely dependable car. It's very good, and it's very good at a very reasonable price, right? So what I'm saying is, with Google Compute Engine, you get the performance of a Bugatti Veyron for the price of a Toyota Corolla. Right? So, jokes apart, but what you're really getting is leveraging and riding on Google's investments, technology, 15 years of experience in building the security around these systems. All of that stuff just comes to you for free. You just take advantage of that and use ride on our investments, so to speak. I keep saying it's highly performant, right? And how do you know? Right? One way is to actually do a benchmark and test and look at different use cases where computational efficiency, network efficiency are all important, right? How many of you have heard of the TerraSort benchmark? Right? The TerraSort benchmark is basically a benchmark where you have 1 terabyte worth of data, it's randomly jumbled up, and you have to sort this data out and put it in a sequence, and whoever does it the fastest has the record. Right? Google currently owns the TerraSort for basically sorting 1 terabyte in 54 seconds. And we did it on about 1,003 instances, right? And this was done on a MapReduce framework with MapR technologies. Maybe I'll just run that to show you what that looks like. It goes very fast, so you gotta be. Okay. There's my mouse around here. Let me just thumb this up. Stop that. Moving it over here. And here we go. So this is basically the attempt, world record setting attempt. Right, so this is the actual sequence running. What you're seeing is a heat map. So when it's green, it's less than 50% CPU utilization. So the map phase is starting, and now it will stop for a while, and then the reduce phase starts. Right, and done. So we're finished the map and the reduce. And if you look at it, if you go and look at the job from the task tracker, so that's 55 seconds, roughly. And if you look at the total amount of data that actually was sorted, that's 1 billion rows, right? So it basically sorted that amount of data in less than a minute. And that's interesting for a couple of reasons. One, to be able to do this, there are a couple of parameters that are key. One, how much computation you get out of each of those nodes. Right? The second one that is important is how much traffic or network bandwidth is available between nodes. And the last one is how fast does your disk system perform to provide the data. On all those three metrics, Google has put in a lot of engineering to make each of those components really, really fast. Now, we have to do this because that's what Google needs to be successful. That's what enables us to deliver a search query in 250 milliseconds, right? So all of those same things that make Google Google enable records like that, right? Now, what is interesting is not just the fact that we broke the record, but what the previous record was doing. So the sort time for the previous record was 62 seconds. They used 40% more servers, 3 times the number of cores, almost 6 times the number of disks, right? And this was an on-premise infrastructure that was built. Do you want to guess who held the record previously? I'll give you a hint. Ex-Googler is now heading the company. Yahoo. So Yahoo held the previous record, but it took them months to build that. It was an on-premise infrastructure. It took them months to build it. And needless to say, the costs involved are also running into the millions of dollars, right? You want to guess how much this record-setting attempt cost on Google? It's a guess. Nobody, it's just, I'm asking you to guess how much money it costs, so don't worry. How much do you think it costs?
$30?
$30?
You only rent 1,000 machines for 1 minute.
Right.
So
Anybody else? $30 going once. Anybody else wants to take a guess? No? $100. Getting warm? At the time the record was broken, we used to charge by the hour. So you spin up a minute for an hour, it'll run for an hour and so on. So at the time the record was set, you could say this cost roughly $1,200 or 2,000, between that range, right? Now we charge by the minute with a minimum of 10 minutes. So now the same record, you could break it for $200. That's the distinction. That's the power of coming on to the Google's platform. Millions of dollars, months of efforts to build this, as opposed to spinning it up in minutes and spending $200 to break the record. Right? So that was about what performance you can get out of Compute Engine, right? What do we offer underneath the covers as core functionality? This is all the system components that come along with Google's Compute Engine, right? There is this notion of a project. Everybody here is a Google developer of some sort? Yes? Are you comfortable with this notion of a project in Google? No? Alright, I'll show you what it is in a demonstration, make it easier, yeah? So there's an abstraction of a project. Think of a project like a container into which you put all the services you consume, right? So it's like that. It's a group, it's a logical collection into which you turn on all these different services that you want to consume, and that's a project, right? Now inside a project we have virtual machines, we have disks, and we have networking services, right? And all of these are accessible through the API, right? Now to manipulate the project, you can use the command line, you can use our user interface on the web, or you can write code. Whatever else you do, all of those talk to the API. I feel like I'm on karaoke right now. All of those talk through the API and allow you to spin up virtual machines, configure networking services and everything else, right? So that at a high level is all the different system components we offer. Let's take the first one, the project, right? So project is basically a container, like I said, and into that you can put all of these different services you consume. This could be Compute Engine services, this could be Cloud SQL services, there could be any of the other services that Google offers like Maps, etc. You can turn them all within that project. And when you create a project, you have the ability to fundamentally assign people to a project and create permissions. So I'm inviting B, and B is a owner level permission. I'm inviting Colin. He could be somebody who can just edit the resources in a project, or it could be somebody else who I just want to give view access to the resources in a project, right? So that's a higher level container into which I add all the different services that I want to consume from the cloud platform. Let me just show you how to create a project and start all of this up. Now, if you have a valid Gmail account, you can try and follow along if you want to, right? Thank you. So let me just quickly go here. Right, perfect. We're moving the displays. That'll be even better. But okay. So let me launch a new incognito window. And the easiest way to do all of this is go to cloud.google.com. Right? If you go to cloud.google.com, this is the page you get to, right? And what you have to do is click on products. Then you get to the product page where you see all of our different products. Click on Compute Engine, right? And if you click on the Try It Now button, I'll click on that now, and automatically it will ask me to log in. So I log in there, and I give my Gmail user account and password, and I click on the Sign In button, and it will automatically create a new project for me. So if I hit on the Create button now, it will create a new project for me. Right? Now I'm just going to click Cancel because I already created a project to show you. So I'll just click on Cancel, and I have a project here. So here is where I see all my projects. So this is what you call as the developer's console for the Google Cloud. Right? Now if you want to come back here later, you can just go to cloud.google.com. And if you have signed in, you can just click on Go to My Console. Or you could just do cloud.google.com console, right? It brings me back here. So inside the console, I have all of these different projects that I have, the requests the projects make. Remember I said everything is an API call, and all of the charges around the project. So I click on the Compute Engine demo project, right? So notice that for every project, we have a unique project identifier and we have a project number. Right? So these are things that uniquely identify your project. Now within my project, I have many different tabs on the side here. Right? So I said there is Compute Engine. Remember that I said this is where you put all these different services together. I have Compute Engine turned on, Cloud Storage turned on, Cloud SQL, BigQuery, etc. How do I turn on these services? I just go to the APIs and authorization window here, and inside here are all these different services that I can use. If to use a service, all I have to do is to click on that button, and that button automatically turns on that service for me. Right? So this way I can add whatever services I want into my project, and then I can consume them. So let me just turn this off because I don't really need it. So I have turned on Cloud SQL, Cloud Storage, Compute Engine, etc. here. Colin talked about Prediction API, all those things. So this is where you go and say, here are all these services I want. I'm going to use all these services to create my application on my project. Now once I've turned those on, I said you can add people to a project, right? So I click on the permissions, I can add people to a project, I can click on add a member to the project, I give that member person's email address, and then I can say what permissions I want to give to them, etc. Right? And this allows me to collaborate with many different people. Colin just mentioned that his project has 6 people across the globe. Your team was a distributed team, you said. Oh, you don't know. Sorry, I misunderstood. My Chinese is not as good as it used to be. So even if you have a distributed team, you could add them into this project and they can all log in from wherever else and still be able to collaborate and work on that project. So that's a quick overview of how you get started, create a project, running through the console, switching on the services you want, and how you go about using it. Right? So let me get back here. Let me continue on then. So once I've created a project, I've turned on Compute Engine in that project, I can now start adding virtual machines to that project, right? So as of today, all of the virtual machines that you can spin up are Linux-based virtual machines. So we have 3 different kinds of machines that you can spin up. There's a standard, there's a high memory type, and then there's a high CPU type. Standard means equal measures of computation and memory. High memory has more memory relative to compute, and high CPU has more computation relative to memory. And that varies, right? Because not all applications are the same. Some applications, let's say I'm doing image processing or video transcoding, those tend to be extremely computationally intensive. I'll give you an example. I have a customer who's building an app where the customer uploads videos, and that videos get transcoded into different formats for delivery on different channels, and those kind of things are best done inside a high CPU node. Right? If you're running a database, for instance, you need to have lots of memory so that the database caches a lot of things in memory and is fast. So maybe a high memory instance is more relatively relevant for that use case. Let's say you're building a classic web server, maybe a standard instance would be a good fit for that and so on. So depending on the nature of the task you're doing, you can choose a different machine type and use that. Any questions so far? No? Now, when you spin up a machine, you spin up a machine in a particular location, right? So we have this concept of a region and an availability group within a region, right? So normally you would spin up in a particular region and an availability group. So as of today, you can spin up instances in America and in Europe, right? So that's where you get to spin up your instances. So what is the difference between availability group A, availability group B, and availability group C? Basically, these 3 groups are isolated. So even if one group goes down, the other group is still available. So if you want to build highly available applications, you want to spread your load across different availability groups so that you have resilience. Right? We have been introducing a lot of new features on the Google Cloud. Fundamentally, we allow you to do things like live migration. What does it mean by that? If you, for example, if you go to another public cloud vendor, if they're doing some maintenance on their data center, they will send you something called a restart notice. They can restart your machine, your virtual machine, because they're doing some maintenance, right? So it's up to you to hurry to figure out how to respond to that. Google implements things like live migration. In fact, we are the only cloud vendor who today does live migration. In other words, if you are maintaining some part of the data center and we think your machine is going to be affected, we will transparently move it to the side. It still keep running. We do the maintenance and then it goes back. So these are things that we call live migration, which affords things like transparent maintenance, which is a huge advantage, right? So I'll just show you quickly how to spin up instances within the console. So I go back to my project here. I go to Compute Engine. The minute I click on Compute Engine, I get different kinds of services around here. One is around virtual machine instances, another is disk, snapshots, images on which I want to build these things, networks I build, all the metadata around these instances, I'll get into that, how to create load balancing, etc. So to spin up a virtual machine, all I do is click on New Instance, right? Now everything that I'm doing from the web UI here, you can do from the command line, you can also do through code, right? And then think about it, you basically write code which spins up infrastructure, shuts infrastructure down, etc. So let me call the GDG demo 1, for example, right? And I give it a description. This is a demonstration machine. Now when I create the machine, I have the opportunity to tag the machine with some metadata tags if I wanted to. A tag is like a label I stick onto the machine, right? So I could say call this tag 1, and whenever I apply commands, I can say apply this command to all instances with say tag 1. And that makes it easier to group machines to apply commands to. I also have the opportunities to attach key value metadata to an instance. And I can handle metadata at the project level, metadata at the instance level, and things like that. And that's useful because using this metadata, you can do dynamic actions within your instance, right? So now I choose where is the zone I want to spin up the instance on. Remember I said it's zones and availability groups. So here I'm going to spin, regions and zones. So I can say US Central 1A or US Central 1B, etc. Right? So let's say I spin it up in US Central 1A. Right? So that's availability group A within US Central 1 region. I get to choose the machine type. I can say standard machine. So the last number at the end of the machine type is the number of cores. Right? So if I do 1, it's 1 virtual CPU. If I do 2, it's 2 virtual CPUs. 4, 8. Recently we have launched 16 cores as well, instances as well. So you can 16 cores and up to 105 GB of RAM if you want it in an instance. Let's say I choose a 2-core instance. So I get 2 core means I get 7.5 GBs of memory. Right? So I choose that. Now when this virtual machine boots up, it needs a boot disk and a boot image, right? So I can basically create a new persistent disk from some pre-existing images that I have. So I have many different options. Here I'm just going to use CentOS. We support all the standard flavors of Linux. So if you want to run it on Red Hat Enterprise Linux, SUSE Linux, etc., it's perfectly feasible. And if I want to add additional disks to the machines, I can. But I'm not going to do that now. I'll leave the networking stuff for explanation for later, right? And when I hit create, now the system will run off, provision a machine, create it in the cloud for me, right? So when I hit create here, so it's creating a machine for me. Right? So it's creating a machine in the cloud for me. And that machine is up and running. So when the flag is ticked, that means the machine is up and running. It's running in zone 1A. That's the external IP address of the machine. I can then now SSH into that machine and do whatever I want. Right? So this is infrastructure as a service. That means I get to manipulate everything operating system and above, right? So I get root access to that Linux machine I just created. It's running in America, and I can do whatever I want on top of that machine. Right? Any questions so far? Yeah?
How many external addresses do I have?
You have basically one external IP address per instance and one internal IP address. So if I click on this one here, so I get an external IP address and an internal IP address. If you want to have multiple IP addresses directed to a single machine, is that what your question is? No?
If I have 100 virtual machines, I have 100 external address.
Yes, for each machine, you will get one external IP address and one internal IP address. Yeah.
Those external IP addresses are dynamic or static?
Good question. So the question is, are those external IP addresses static or dynamic? You have an option. So you can provision static IP addresses, and by default you get ephemeral IP addresses. That once the machine goes down, that IP address can be reused.
So how long will the dynamic IP address change?
No, it won't be changed. Sorry, you shouldn't think of it like DHCP, that's not what it is. This is an IP address which is temporary. As long as your machine is running, it will have that external IP address. If the machine shuts down, then if some other machine springs up, we can give that IP address to that machine. So for the life cycle of that machine, it will hold that IP address.
I'm using the same but at different time. So I will get different internal IP.
If you don't ask for static IPs. But you can ask for static IPs, and that will be standard. You can assign the same static IP address to that machine. It's a good question, thank you. Any other questions? Right. So basically, everything that I just did, I can do as an API call, and this would be the RESTful API call that makes that happen. So here is the RESTful API call to basically get into that machine, and here is the RESTful API call. Here's the utility call that I've used to log into that machine. So what is the time? So in the interest of time, I'll just skip secure shelling into it, and I'll continue on and talk more about the rest of the stuff. Right? So the next one is around storage. So I've created virtual machines. I can attach storage to that virtual machine, right? So this is block storage. There are many different options, but the key one is what we call as a persistent disk. Persistent disk means even if the instance goes down, the data is still saved. Right? So Google basically gives you a very highly performant persistent disk system. You can create the persistent disk, and it is bound to the zone in which you are creating that disk. The persistent disk can go up to 10 terabytes in size, and that's 10 times anything any other cloud provider can provide today. Right? And with one machine, I can put up to 16 disks in there if I wanted. Right? So persistent disk is where you would store things like your database files. These are all mission critical data that you want to store. Now, whatever performance you get out of the Google persistent disk is at encryption. Right? Security is important. So all of the data that is going into the persistent disk is encrypted at rest. Nothing is stored in clear in the rest on the persistent disk. Right? You can attach a persistent disk as a read-only disk to many machines, or it can be read-write to a single machine. That gives you opportunities, right? For example, I have customers who, instead of trying to create a huge NFS system to share data, etc., read-only data, they put it onto one PD and then just mount it on multiple machines, and automatically they get read-only functionality to a central piece of data, right? So that's a good option if you have some data that gets shared and distributed across multiple machines. Rather than do complex NFS stuff, you could just load it onto a persistent disk and mount that persistent disk on all those machines. Then automatically that happens. It's what we recommend for the root disk, right? Obviously. Right? You get extremely consistent performance with the persistent disk. So on the diagram you have different volumes here, and you have IOPS. These numbers, by the way, have gone up even higher. So I will check the web to see what the latest IOPS numbers are. But what we have done recently is to make a change that the amount of IOPS you will get, IOPS meaning IO operations per second. Right? If you buy a 3 terabyte hard disk from the market, they can do roughly 30 to 40 read IOPS per second. IOPS meaning reading random 4K disk blocks from different places on the disk. And that is always governed by seek time of your disk, right? So if you buy one from the market, you get maybe 30-40 IOPS per second and random read IOPS write IOPS per second. But our disk provides about 240 read IOPS and 600 write IOPS out of the gate. And these numbers have gone even higher. And we have made one recent change where we have said, if you want more IOPS, you just provision a bigger disk. So you put a bigger disk, you will get more IOPS. So I think the maximum you get is for an 8-core virtual CPU with, I think it's something of the order of 1,500 to 2,000 write IOPS you get per second, which is a lot, right? You can check on the web for what the latest IOPS numbers are, and there is a very nice table on the Google website which actually shows the IOPS scaling with disk size, right? Maybe I'll just look for it right away. Google disk persistent disk IOPS. So, as you will see, the low persistent disk model, the IOPS just included in the price of the space, and there you go, we've raised the overall caps. So it's now 2,000 random read IOPS, 2,400 write IOPS. So I just said 600, the numbers have gone up even higher now. And you get 180 megabytes of streaming reads and 120 megabytes of streaming writes. That's a lot of capacity and performance, which you don't usually get from others. We are able to deliver that because Google has the engineering and the scale to pull off these kind of performance levels. Oops. Right? So how is that underneath the covers working? Underneath the covers, what we do is basically shard it and use multiple disks in parallel, and we achieve this kind of performance by doing a fair amount of parallelization of your write workloads and your read workloads. So every time we get a write to a disk block, we spread it out across multiple different machines, and we have multiple copies of all of the data with encryption and checksums and everything, so that your data is extremely resilient. And when we read from the fastest copy. So underneath the covers, this provides you a lot of resiliency of your data, security of your data, and at the same time, by doing random write optimizations, we can give you extremely high performance. So next topic is around the network, right? So we talked about computation, we talked about storage, Now we talk about the network itself. So within every project, I can create up to 4 networks. By default, there is a network that is created which is called the default network. Right? So I can, within my project, create up to 4 networks, but I can spin up instances in a particular network. Right? So what that allows me to do is to spread my instances across different networks and separate my application into different tiers, right? So normally people will have a dedicated network for, say, web front-end servers, and another network for the middle tier, and another network for the back-end database, so that you have security, even higher security, isolating all these different parts of your system. So in this example here, I have one network which I call a DB network, one network that I call a web network, and all my web instances are running in my web network, and my database is running in my database DB network. And I create firewall rules which allow the data to move across these networks. And I can say those firewall rules will accept only traffic from these IP addresses or these tagged instances and so on. So I can really secure my network and my infrastructure really, really well. And all of the networking resources that we provide are currently IPv4 based, right? By default, we block traffic on port 25. Anybody wants to take a wild guess why? Obviously, we don't want people sending out spam messages and things like that. So obviously, we block port 25. But there may be genuine reasons why you need to use port 25. Then you just create a support case, and then support might be able to help you with that. But by default, we just block all traffic on port 25. Right? So the other nice bit is that when you spin up, networking in the Google Cloud Platform has been built into the system from the ground up. It is not an afterthought. Like you go to some other public cloud provider, you have to build this concept of a virtual private cloud. Right? So you have to isolate your instances. In Google, when you spin up instances in a project, they're automatically isolated from everything else, and they form their own isolated networks. Right? And that is available by default out of the box. You don't have to do anything special to make that happen. And that's a huge advantage, right? And another interesting aspect is that I can fundamentally use the machine name to perform host resolution internally. What do I mean by that? If I go back to my console here, sorry, not this one. If I go back to my console here, right, I have one instance in America. Now within the same project, if I spin up a new instance, I'll say GDG demo 2, and let's say I'm going to spin this instance up in Europe, right? And again, I'll choose a CentOS image. I'll just use a 2 CPU machine. I can do any number I want. So it's GDG demo 2, and I hit create. Now it's creating a new instance, right? And we'll just give it a couple of seconds for this instance to show up on the console. So it's just loading up. Now I have one machine in US, one machine in Europe. They're part of the same project, and they can talk to each other just by using their hostname. It's very difficult for you to do this in other public cloud providers because they don't have the fiber optic backbone. In other cloud providers, if you spin up one instance in their America data center, spin up one instance in the Europe data center, and you want these two instances to talk to each other, you have to build an IPsec tunnel, you have to build a VPN, or you have to build additional logic at the application level to do that. You don't have to do any of that in Google because they are now connected by Google's fiber. So they're part of the same project and they can just start talking to each other, isolated from everybody else. And that's a huge, significant advantage, particularly if you're trying to build applications that you want to take to. Because this rides on top of Google's vast investments in fiber that actually make this happen. That's one aspect. The second aspect is even if you try to do this with other public cloud providers, all of that data is going on the public internet, right? And if it's going on the public internet, there's a lot of quality of service problems with variable latency and things like that. You don't have those quality of service problems in Google because everything runs on Google's fiber. You will get consistent ping times between your Europe instance and your America instance because it's on our own fiber. And that makes new kinds of distributed architectures possible where previously you couldn't do those things, right? And that's pretty significant advantage as well. Okay, let me continue on. By the way, Colin, how am I doing for time? I'll wrap it up in another 15 minutes. Okay, thank you. So once you spin up instances, you have capabilities of doing things like load balancing. It's a very classic thing you want to do, right? You have 4 or 5 Apache web servers that you're running and you want to distribute the load across those things. So we provide things like load balancing as a service. So how does that work? Basically you spin up different instances and you define something that we call a health check. The health check is basically how do you know that instance is okay, right? In this example, I'm going to request a path, a URL path, and if I get a response on that URL path, the 200 message, I know that that instance is okay, right? So I spin up instances and I define a health check, and I bring these two together in what is called a target pool. So a target pool is a collection of instances with a health check so that I know whether the instances are okay inside that pool. And once I have created this pool, I created a forwarding rule which distributes the load across those instances. So if I have 3 web servers, right, I will spin up 3 instances, right? I define a health check and I connect them all into one target pool and I define a forwarding rule to that target pool. So whatever inbound HTTP traffic that comes gets spread across those 3 web servers. So all of these things are available as a service for you. And these take advantage of all of our engineering and investment. Recently, we actually demonstrated one use case where we had 1 million requests per second being load balanced, right? And that kind of things are only possible on Google because this is the same thing that helps load balance all of our other services as well, right? And that's what we're taking advantage of. And we are announcing more and more improvements to this as well. So you don't have to do things like pre-warm requests and so on. And the final one is around API. Everything that you see that I demonstrated from the UI and the console, and you can do through code. Because all of it is just a RESTful API, right? It's a RESTful API with JSON, and you can write the code and execute every one of these from an API and whatever programs that you might run. And when you do that through code, you can actually use other parts of the Google platform to spin up instances, shut down instances, and things like that, right? For example, if you take into account our App Engine platform as a service, I can do things like have App Engine control Compute Engine, spin up instances on Compute Engine, etc. So since it's code, you can just write code to manage your infrastructure. And that's completely feasible and plausible as well. Right? So let me just show you the command line, for instance. Just clear that. Everything I did from the console, I can do from the command line. So I can do gcutil, which is Google Compute Util. And it's very simple to install this. You go to our website, there's a package we have called the Cloud SDK. And when you install the Cloud SDK, you get all of these different components for you. For example, if I do gcutil list instances, it's going to list all of the instances I have. So this is another project that I've defined as a default project. So these are all the instances that are running inside another project that I have, right? So I can run any of these commands in here as well. So as you can see in this project, I have instances in America, instances in Europe. Supposing if I want to see all the images that I have, I use gcutil list images. It lists all of the images, source images that I have. If I do gcutil add instance temp demo, I can now even create a new virtual machine straight off the console as well. Right, so now it's saying, where do you want to spin that instance up? Let's say I spin it up in US Central 1A, and it says what is the type of machine that I want. Let's say I want 2, and what is the operating system image that I want. Let's say I choose Debian this time. Off you go. So what I did from the UI, I'm doing from the console, and off you go. Oh, sorry, somebody else has already created a machine called temp demo, right? So that's a collusion, so I'll have to read on that. But you get the idea. Whatever I do from the console, the web console, I can do from the command line, I can do using API, etc. So if I go back to my console here, and I look at networks, as you can see in this one I have only one network. And if I go inside there, I have different firewalls that I can create. I have one for allowing internal traffic. If I wanted to create a new firewall that allows HTTP traffic, I just say create new HTTP firewall. I can specify the source address ranges, and I can say port number 80. If I have any source tags or target tags, etc. And now I've created a HTTP firewall that allows inbound traffic on port 80. Right? So I can create all of these different things and then create my application infrastructure in any way, shape, or form that I choose. If I want, I can create a new network within this project. So I can create, say, a database network and spin up only database machines in there and isolate them and so on. So all of these things are possible because we have done a whole amount of work to make these virtualizations possible, and you can take advantage of them. Now I said I can basically control Compute Engine from API, right? So let me go to another project I have here. So this is another console project I have here. And if I go in and look at the Compute Engine instances here, I have a couple of instances here, but this is my App Engine app, same platform that Colin used to demonstrate his big data application. How do I know it's an App Engine app? As you can see, it says appspot.com. Now I'm going to use code inside this app to spin up Compute Engine machines, right? So if I specify 10 machines here and click on start, what that code is now going to do is to go run off and try and create Compute Engine machines. So as the color changes, the system is going from being provisioned to getting ready. So when it's green, that means the machine you can SSH to already. Now you can see it just took me 10 seconds to start 10 machines. Right? I can start 100 machines in like 60 seconds. There was a customer case where I actually demonstrated spinning up a Hadoop cluster using a Hadoop framework with 200 nodes in 6 minutes. So that kind of speed, instant startup speeds, is simply possible because Google knows how to get that done. So if I go back to my project here, I see all these machines that I just spun up. Right? And that's the advantage of the platform. Extremely fast instant startup time, high performance, and an ability to manage these from code, from console, from the UI. Right? So, any questions so far? Yep.
So how can Google achieve such a extremely fast
Performance.
for provisioning a new VM? So how can Google achieve that?
Yeah, we've done a lot of work, and if you go to research.google.com, a lot of work has been published around that. There are lots of innovations we have made, and we have published them as well. There are things like internally, we do very smart things like most public cloud infrastructures if you go, but in the virtualization they mix storage with computation with network, right? And that can cause problems because if one consumes a certain resource too much, it can slow other machines on the same thing.
Okay. Are you using a tool standby there?
No.
The new request or just real-time snapshot or something?
We spin it up because we have done a lot of optimization on the virtualization layer as well. And there are innovations like what we call Spanner, which help with large-scale cluster management and things like that. So if you go to research.google.com, we have documented some of these. But fundamentally, it goes back to the Mac versus PC example, because we can optimize the whole stack. We can optimize everything, including the virtualization performance, to make things go really fast. Any other questions? Yep.
As you mentioned about the scale. Is it very easy to scale in Google Computer Engine? Can you show how easy to scale it up or scale?
I just spun up 10 instances in 10 seconds.
I just mean if I want more computer power,
Right?
I just set up one VM, it's all done, or I need to apply.
It depends on your application, right? So for example, the classic scaling case is depending on user web load, I want to spin up more web servers, right? So the way that works in Google Compute Engine is that you have App Engine, so that process is a two-step process, right? You need somebody monitoring for load on the virtual machines and giving events about load, right? So let's say I have one virtual machine as a web server and the load is becoming 70% on the CPU, for example. And I want to say if it hits 50%, I need to spin up one more to make things better, right? So you need an agent on the virtual machine which is constantly creating and monitoring parameters. You need an orchestrator who is looking at those parameters on a periodic basis and saying, wait, this signal is this level now, I will spin up one more, right? And the way that works in Google Cloud Platform is App Engine is the orchestrator. And on each of the machines, we have an agent framework which will publish whatever statistics you want to make that decision on. And that's how that works. Does that answer your question? Very good question. Thank you. So let's maybe wrap it up. I think we're getting close to the end of the day and I'm pretty sure you're all very tired. So if you compare our performance to real world performance from out there, right? And this is not done by us, it is done by Sebastian Stadl from Scalar, and they compare Google's performance, computing in performance, to another public cloud vendor's performance. The ones in blue are Google, and the ones in yellow are another public cloud provider. You can figure out who that is if you Google that article, right? So if you think about scalability and things that make it different, on all those things that make it different, Google comes out pretty well. In terms of latency, you can see we're pretty low, easily a factor of 4x lower than what anybody else can provide. In terms of how much regional bandwidth is available to your nodes, that's easily an order of magnitude better. And if you look at consistency of performance in terms of instance creation time, as you can see, you can expect a lot of variability from other public cloud providers, but Google is pretty consistent on that one. Why is that all possible? Because Google has to solve these problems to make Google Google. Right? Otherwise, we don't be Google, right? So we have put in all of that engineering and infrastructure to solve these problems, because cloud computing and building scalable cloud platform infrastructures is in our DNA. That's what makes Google Google. And all we're doing is now taking that DNA and that engineering and giving it to you and say, go off and build what you want to build. Right? So just to wrap up, we do things like sub-hour billing, we do 1-minute increment billing, we have more features that I can't really touch today, but you can do all kinds of advanced stuff like creating VPN servers, creating gateways, etc. We have ability, and by the way, all of our services have things like ISO 27K certification. All of these things are independent third-party certifications too, which guarantee our security of our infrastructure. And we have introduced a whole bunch of new services. We have introduced some micro shared core instances as well, if you needed them. But the key is, it's infrastructure using Google's data centers. And what you get from us is consistency and performance at scales that is very hard to get elsewhere, right? So Google, just take a step back and ask yourself what applications you would build if Google was your data center. In other words, you don't have to spend $3 billion a year to build a massive, globally scalable infrastructure. You have that infrastructure to play with. What applications would you build, right? There are many different IO talks here. There's documentation that you can find, but I think this might be a good place to stop, and I'll take any additional questions you have. And this was basically one part of the Google Cloud Platform, which is Compute Engine, which we got into a whole lot of detail. But there's more stuff in there. I highly encourage you to go to developers.google.com, take a look at the compute section, and also spin up your own instances and test them out, right? Do you have any questions that I could potentially answer or help you with? Yeah, there's a question there, the lady.
And before you said how good is the Google Fiber, do you have it in Taiwan right now?
We opened a Google data center in Taiwan, but as of today, you can spin up instances only in Europe and in the US. But what I can tell you is keep a lookout.
The data center in Taiwan, I think it may be in the Zhanghua.
Yeah.
The data center is building now, right?
We launched the data center already,
Okay.
but the same question as us, can I spin up an instance in Taiwan, right?
Yeah.
And my answer to that is, as of today, you can do it in Europe and in America, but watch this space very carefully.
Thank you.
That's the best I can tell you. Any other questions that I can answer? If nothing else, then thank you very much for your time and hand it back to Colin.
好，谢谢大家。那就是接下来就是交流。哦，我补充一个，就是刚刚你问的那个问题，就是你刚刚问的是说，就是有没有像 Cloud Watch 那个东西，对不对？就是你用 AWS Cloud Watch 去 monitor 就是 computer engine 的那地方，它有，然后它就叫 Orchestrator。然后他刚刚讲的 Orchestrator 你不一定要自己做，就是你去 Google Cloud Platform 的 GitHub page。它里面有个就叫做 Google， 对，就有那个 Solution Orchestrator， 那里面有一个 Java 写的 application， 它就是你 deploy 上 FH 之后，它就变像 Cloud Watch 一样的，你就可以直接去监控。它里面有设定的，你就设定那个流量，然后它就可以帮你监控。你只要 deploy 就好 ，deploy 然后设定打上去之后，它就会帮你去监控那个 instance， 然后跟里面要设定哪个地，你要用哪个 disk 去弄，你要用从哪个 disk copy 从哪个 snapshot， 你都可以设定。设定完之后，流量自动起来，它就自动生成你想要的机器。它讲的是 Orchestrator， 不是一个 project。GitHub 那边找到，所以 GitHub 搜寻 Google Cloud Platform 就找到。